Hey Hampshire chemistry students, so today we are going to be talking about two-step stoichiometry. In the past we've done one-step stoic problems where we've gone from just moles to moles. Today we're going to expand on that and we're going to incorporate a mole to mole conversion along with either a step in the front or a step at the end. So you should all have your worksheet in front of you. So some background information. One important thing that we want to remember, okay, we've been doing this part, right, we did this for a really long time, since we got back for our second semester, so that 1 mole is equivalent to 6.02 times 10 to the 23rd molecules, which is also then equivalent to the molar mass in grams, which is also equal to 22.4 liters of gas at STP. And for those of you who may not remember or need a little refresher, standard temperature is 0 degrees Celsius and standard pressure is 1 atm. Okay, so what we are going to do, we're going to take this, like I said, a step further. In previous problems and information we've learned, we've gone from different units. We're converting between units. This time we are going to be converting between moles, so we're changing the elements in our mole to mole step, but then we're going to add on to that, and then we are going to go from moles to moles of a different element to a mass or a volume, for example. So here we have a very generic equation. So moles, we have A plus B gives us C, right? So we can go from moles of A to moles of B. And with that, right, so this is what we've talked about the past few days. We went from moles of one element to moles of a different element. We can either add steps in at the front, where we are starting with possibly, say, a mass in grams, or a volume in liters, or particles, molecules, or atoms, right? We could also do this at the end where we go from moles of one compound to moles of a different compound, and then convert moles of B, for example, to grams, volume, or particles, molecules, or atoms. Okay? So let's put this into action and take a look at a practice problem. So if we look at our practice problem here, let me zoom in a little bit. So if we take a look at our practice problem, we need to calculate the mass of aluminum oxide that is produced when we make 3.75 moles of aluminum that have been burned in oxygen. Sorry for the shakiness. We're looking a little blurry here, so I just want to clear up our picture. There we go. Hopefully that's better for those of you watching at home. So again, we are starting with moles, 3.75 moles of aluminum. Okay, remember aluminum is Al. And we are trying to find the mass of aluminum oxide. So grams is our unit of Al2O3. Okay, so we have our equation. I'm going to go ahead and place this here and we'll talk through this. So the equation that we have aluminum plus oxygen. Remember, oxygen is a diatomic, so we need to be O2, yielding that aluminum oxide, so Al2O3. So the first step, just like when we did one-step stoichiometry problems, we need to balance our equation first. So this is an unbalanced equation. So let's go through and balance this out. Let's first take a look at the oxygen. So oxygen, we have 2 oxygen atoms in the reactants and 3 in the products. So if we multiply this side by 3, that gives us 6 total oxygen atoms, right? Those charges are going to cancel. And on this side, we have 3 oxygen atoms. If we multiply by 2, we're going to have 6 oxygen atoms. So we have 6 and 6, so they are balanced. They're going to cancel each other out on both sides. However, we have this aluminum here, so if we are adding we're multiplying by 2 to our oxygen here, we also have to multiply these aluminums by 2. We already have 2 of them, so 2 times 2 will give us 4 aluminums, which means this aluminum here, we're going to have to multiply by 4. Okay? Remember that the coefficients, these numbers out front, are going to give us our mole ratio. Okay? So, let's continue on. First, we're going to create the bare bones of our problem here. So we are going from the moles of aluminum to the moles of aluminum oxide, then to the mass in grams of aluminum oxide. Okay, so this is just a very generic basic setup of what we are going to be looking at in our 2-step Stoich problem. So we have 3.75 moles of aluminum. Okay, actually, let me backtrack for 1 second here. So this arrow represents our mole-to-mole conversion. We are going to get that molar ratio from our equation, right? That balanced equation up top. We go from the moles of aluminum oxide to the grams of aluminum oxide. We're going to need a molar mass. Okay, so we can think about this as this is the first step. The first arrow is showing us our first step that we have to take. The second arrow is our second step in our problem to achieve our final answer in grams of aluminum oxide. So we'll set up our problem, right? We'll have step 1 and step 2. So in our first setup, we are trying to go from moles of aluminum to moles of aluminum oxide. So units, moles of aluminum, so moles of Al. We're going to go to our balanced equation, and we're going to see that 4 is our coefficient. So we have 4 moles in that mole ratio. Then, if we take a look at the top part, right, our moles of aluminum are going to cancel. In the top half, we need moles of aluminum oxide, Al2O3. All right, we go to our balanced equation. We see that this is a 2 here. So our coefficient, our mole ratio, if we are going from moles of aluminum to moles of aluminum oxide, it is a ratio of 2 to 4. Okay, so next step, we're going into the part where we need to convert our moles of aluminum oxide to a mass in grams. So this unit here, we're going to drop it down, moles of Al2O3, and then our last unit that we are looking for is going to be grams of Al2O3, or that aluminum oxide. Okay, so this part here, right, this is what we were doing for a really long time, from beginning of January, when we came back after our end of this first semester. We did some regular mole conversions or molar conversions, right, relating back to this really big conversion factor that we talked about and how all those are equal to each other, So the first thing we know we're going to have to do is this grams of aluminum oxide, we're going to need a molar mass. So I've already gone through and calculated that for us. So let's take a look, right? Remember molar mass, we need to multiply by how many we have. So we have 2 aluminums. The molar mass of 1 is 26.98 grams. So multiply by 2, you have 53.98 grams of aluminum. Oxygen, there are 3 of those in our formula of aluminum oxide. Multiply by 16 gives us 48 grams of oxygen. We add all these together, and our total molar mass for aluminum oxide is 101.9 grams per mole. Okay, so we know we can plug that in up here, 101.9 grams of aluminum oxide. Okay, I'm going to remove that for a second. And then, right, knowing what we know about our big conversion factor with molar conversions, we know that 1 mole is equivalent to the molar mass in grams. So down here in the bottom half of our second step, we're going to have 1 mole of aluminum oxide. Okay, remember, this is coming from our mole ratio, our balanced equation. This is our molar conversions with our big conversion factor that we have listed at the top of our page. So if you go to your calculator and you plug all this in, you would see that 3.75 times 2 moles of aluminum oxide times 101.9 grams of aluminum oxide, all divided by 4 times 1, will give you an answer of 191 grams of aluminum oxide. Okay, so hopefully, as you were following along, maybe you took a second to pause the video and see if you can solve the problem on your own. So as you see here, right, we're taking what we were learning the first chunk of the semester, right, this molar conversions using our step 2, or this big conversion factor that we've talked about a lot, and we're combining it with what we've learned recently with those mole-to-mole conversions in our stoichiometry. So here we were converting from different elements, aluminum to aluminum oxide, but then taking that and converting it to a completely different unit altogether, not just the element, but we're going from moles then to grams. Okay, so I'm going to take a quick flip to the back side and kind of talk through what we're going to see here. So the back side is a lot of the same thing, okay? At least this time you don't have to balance out the equation, so you're welcome. You don't have to go too in-depth. Some of these equations, if you take a look, some of them are a little crazy. So you have a balanced equation, and you're not necessarily always going to start with a mole-to-mole conversion. You may start with a mass to moles conversion or something along those lines where you're not necessarily doing mole-to-mole first. So just make sure you're paying attention to what you're starting with and what you're trying to find. So in our back page, right, let's take a look really quick here at A. If we have manganese atoms, we're trying to find how many manganese atoms have been released if we have 54.8 moles of our manganese oxide, okay? So again, make sure you are taking your time with this work. It's not about a race, it's just to see, you know, if you can figure out how to combine what we've been doing and what we've been doing recently into one big problem. Balance equations are given. Again, this conversion factor is extremely important, along with knowing that mole to mole is the heart of stoichiometry, right? This is extremely super important. We cannot go from one element to another without this mole to mole conversion in our balanced equations, okay? So if you have any questions as you are working, feel free to come see myself, or if you're watching from another one of our great Hampshire chemistry teachers, you can always go see them as well. So without further ado, I bid you good luck and have fun with your two-step Stoich problems.